This is the 21st video in a series devoted to differential equations. And with this video, we're going to start looking at systems of first order linear differential equations. So by a system of differential equations, I mean we've got this collection of differential equations, each for a function y1 up to yn. And that system is in terms of all of the yi's and a forcing function, or a collection of forcing functions f1 to fn. So let's notice this first equation says that y1 prime is a11 of t times y1 added up to a1n of t, yn plus f1 of t. And then we've got similar equations for the derivatives of all of these yi's. So let's notice that we could put this system of equations into a matrix vector equation as follows. So we've got this vector made of the derivative of the yi's is equal to this matrix made up of the functions aij times this vector made up of the yi's plus this vector made up of the f's. So that motivates us to put this all together into one object. And so we've got vector y prime equals a times vector y plus vector f. So that collects all of this information into one place. And then we've got a theorem that talks about the uniqueness of such solutions to these differential equations. And that says that if we have an initial condition, notice our initial condition will be a vector here. So y evaluated at t naught is equal to some vector k. Then this differential equation has a unique solution as long as we're on an interval where a of t and f of t are continuous. And of course, this initial point for our initial condition also has to come from this interval. So this is pretty similar to other existence and uniqueness theorems that we've seen before, and we're not going to prove that here. What we will do is start with an example which highlights the duality between the order of a differential equation and maybe what I'll call the rank of a system of differential equations. So here this is a second order differential equation, and we'll see that this second order differential equation can be turned into a system of two first order differential equations. So let's see how that might go. We'll start with y double prime minus 6y prime plus 5y equals sine of t. And let's set y1 equal to y. So that's what we're going to start with immediately. And then we'll also set y2 equal to y prime. So notice that immediately gives us one of our systems of equations, and that system of equation will be y1 prime equals y2. And so that's based off of this first assignment that we made, and then maybe plugging that first assignment into this second assignment that we've made. I guess I should not have an implication arrow here, I just should have a comma. So we're setting y1 equal to y and y2 equal to y prime, and that gives us this first equation, which is notice a very simple version of the first equation up here. So now let's try to get the second equation. So let's notice that y2 prime is the same thing as y1 double prime, which is the same thing as y double prime. But we can solve that in terms of y prime and y and this sine function using our given differential equation. This is equal to minus 5 times y, and then plus 6 times y prime plus the sine of t. But now let's rewrite all of this in terms of our y1 and y2. So we have y2 prime is equal to minus 5 times y1. Recall that y is equal to y1. And then plus 6 times y2. Again, recall that y2 is equal to y prime. And then we'll have plus the sine of t. So that would be our second equation. So putting this purple box and this blue box together, we see that we have a system of two equations. Now we can put this into a matrix vector equation as follows. Maybe we would assign vector y to be y1, y2, and then we can notice that the derivative of this vector valued function is equal to, let's see, 0, 1, minus 5, 6 times vector y plus the forcing function, which is vector valued and it has entries 0 and sine of t. So there, we did it. We just translated this second order differential equation into a nice vector valued first order differential equation. Okay, so now let's see if we can go in the other direction, and maybe that will give us some insight on how to solve these types of differential equations. So like I said before, now we're going to start with a system of first order differential equations, see if we can translate this into a second order differential equation, solve that second order differential equation using the techniques from earlier in the class, and see if we can come up with what will be a general format for solutions of these types of equations. Okay, so let's see how we might do this. Let's start the same way that we did before. So let's set y equal to y1. Okay, now since we're aiming to have a second order differential equation, let's look at y double prime, which ends up being y1 double prime. But y1 double prime will be equal to 2y1 plus y2 prime, just based off taking the derivative of this first of our system of differential equations. That ends up being 2y1 prime plus y2 prime. Okay, so that's good. So now let's rewrite that with stuff that we're kind of okay with. And what I mean by okay with, we're okay with y1, and then see if we can maybe fix the parts that we are not okay with yet. Okay, so let's maybe rewrite this as 2y prime. Given that we're saying that y1 is equal to y, that would be this term right here. And then let's start to fix this y2 prime. And we can do that with our second differential equation. So let's note that this y2 prime can be rewritten as y1, which is y, plus 2y2. So let's bring that down here. So we have this is plus y plus 2y2. Then what can we do with this y2? Well, let's note that we can use this first of our system of equations to rewrite that. So let's do this. So let's take this y2 and we'll replace it with, in this case, y1 prime, which is y prime, minus 2y1, which is minus 2y. So we're left with something like that. Okay, so now let's see what we have in the end. So we'll have 2y prime plus another 2y prime. That gives us 4y prime. And then we'll have y, and then minus 4y. So subtracting 4y will give us negative 3y. Now let's bring this y double prime down and see that we indeed have a second order linear differential equation. Let's rewrite that in the standard format. So that's y double prime minus 4y prime plus 3y equals 0. And in fact, what we can do here is just go ahead and write the solution down based off of our solution techniques before by finding the roots of a certain polynomial. I won't go through those details. But what we'll end up with is y, which is the same thing as y1, equals some constant c1 times e to the t, plus some constant c2 times e to the 3t. And that's because the roots of the corresponding polynomial here are 1 and 2. So that's y1. So now we can calculate y2 by using this equation right here. So remember that y2 was equal to y prime minus 2y. In other words, y1 prime minus 2y1. I won't work out the details, but what we get is y2 is minus c1 e to the t plus c2 e to the 3t. Again, that's from putting this equation right here for y2 using our y1 that we already have here. So if we were to go ahead and put this in matrix vector form, we would have something like this. So we'll have y vector is equal to, let's write maybe c1 e to the t, and then we have vector 1, negative 1, and then plus c2 e to the 3t times vector 1, 1. Great, and that would be maybe a nice final way of writing this solution down. Okay, so let's take some motivation from the fact that it looks like our solutions are exponentials, which makes sense because this is essentially like a generalized version of our favorite first order differential equation, which is y prime equals k times y, which had an exponential solution. So let's see if we can use that solution format guess to come up with a more universal way of writing down solutions for these types of systems of differential equations. So now that we did this kind of crazy backwards method of finding a solution to this differential equation, let's use that solution format that we found and see if we can come up with something a little bit better. So let's assume our solutions are of the following form. So we'll have y1 is equal to x1 times e to the lambda t, and we'll have y2 is equal to x2 times e to the lambda t. And here we have x1 and x2 are real numbers. I'm using x1 and x2 instead of c1 and c2 to make this look like a system of linear equations from linear algebra coming down the line. Okay, so now let's plug those guesses for our solution into our differential equation and see what that leaves us with. So y1 prime will be equal to x1 times lambda times e to the lambda t equals 2x1 e to the lambda t plus x2 e to the lambda t. Okay. And then likewise, we'll have x2 lambda e to the lambda t is equal to x1 e to the lambda t plus x plus 2x2 e to the lambda t. So that's just plugging those y1s and y2s in. But now we can simplify by dividing both of these equations by e to the lambda t, given that e to the lambda t is never 0. So that'll cancel out all of these exponential functions and leave us with simply a system of linear equations. So let's maybe move it around so it looks like a homogeneous system. Notice moving this x1 times lambda to the other side of the equation will leave us with something like 2 minus lambda times x1 plus x2 is equal to 0. And then likewise, moving this x2 times lambda to the other side of the equation will leave us with something like x1 plus 2 minus lambda times x2 equals 0. But if we remember linear algebra, a nice way to do this is to rewrite it as a matrix vector equation instead of a system of equations. So let's do that. That turns into the matrix vector equation 2 minus lambda 1, 1, 2 minus lambda, hitting the vector x1, x2, and giving us the 0 vector 0, 0. Okay. But let's note that if this vector x1, x2 turns into the 0 vector when multiplied by this matrix, that means it's in fact in the null space of this matrix. But being in the null space of this matrix means this matrix is not invertible. But if this matrix is not invertible, that means its determinant is 0. But the fact that its determinant is 0 means that we can set up some sort of nice equation for lambda. So let's do that. So we know that the determinant of this 2 minus lambda 1, 1, 2 minus lambda must be equal to 0. But that gives us the equation 2 minus lambda squared minus 1 equals 0. Which we can easily solve, and we'll see that lambda is equal to 1 or lambda is equal to 3. Those are our two possibilities. Okay, so now let's bring those possibilities up along with this matrix vector equation and go from there. Okay, so on the last board we determined that if we started with the following maybe guesses for solutions of our system, then the lambda in the exponent there and the numbers x1 and x2 satisfied the following system of linear equations exhibited by this matrix vector equation. Furthermore, we saw that lambda was either equal to 1 or lambda was equal to 3. Those were the two possibilities. So let's work through each of those and see if we get values for x1 and x2. So let's start with lambda equals 1. So what we'll do is plug lambda equals 1 into this matrix vector equation and solve for x1, x2. So that leaves us with 1, 1, 1, 1 times x1, x2 equals the 0 vector. But immediately we see that tells us that x1 plus x2 is equal to 0, which means that x1 is equal to negative x2, or maybe x2 is equal to negative x1. Perhaps that's how we would like to write this. And now let's look at the other case when lambda is equal to 3 and see what we get in that case. So in the case that lambda is equal to 3, our matrix vector equation turns into negative 1, 1, 1, negative 1 times the vector x1, x2 equals the 0 vector. That gives us the equation, which is like x1 minus x2 is equal to 0, which tells us that x1 equals x2. So we have something like that in this case. And then by the principle of superposition, if y1 and y2 defined by lambda equals 1 is a solution and lambda equals 3 is a solution, then a combination of them is also a solution. So that gives us y1 equals something like this. We'll have x1 e to the t plus x2 e to the 3t, and then y2 is equal to minus x1 e to the t, and then plus x2 e to the 3t. Where of course I was careful here in that these xi's are independent of each other because they're coming from a different set of equations. So the important thing here is that the coefficients of e to the t have opposite signs based off of what happened in this orange, and the coefficients of e to the 3t had the same sign based off of what was happening in the blue. But we'll see that this is exactly what we got with our previous method. So we have y vector is in fact equal to, let's write it as x1 e to the t times the vector 1 minus 1 plus x2 e to the 3t times the vector 1, 1. Okay, so let's maybe finish this example off by looking at the structure of this differential equation with relation to these lambdas and these vectors. For those of you that have a strong background in linear algebra, you might already see what's happening here. So with both of our solution strategies, we ended up with the following solution to this system of differential equations. Let's first notice that we could rewrite this system of differential equations in the matrix vector form as follows. We have the derivative of the vector valued function y is equal to this matrix 2, 1, 1, 2 times our vector valued function y. But let's see if we've got any relation between these coefficients of t, these vectors here, and this matrix 2, 1, 1, 2. But if you recall back to the calculations we did on the last board, those were exactly the calculations that we would do if we were interested in finding the eigenvectors and eigenvalues of our matrix 2, 1, 1, 2. Okay, so let's maybe point that out. So let's take this number 1 here and then this vector here, and note, maybe we'll color code this with a green square, that lambda equals 1, and then maybe we'll call it lambda 1 equals 1 and v1 equals 1 negative 1 is an eigenvalue slash vector pair of our matrix 2, 1, 1, 2. And then the same thing's going on with the other bit. So this number right here, 3, which I'll maybe highlight in this magenta color, and this vector, which I'll underline in this magenta color, and then I'll color code that over here. So this lambda, which I'll call 2, is equal to 3, and then this vector v2, which is the vector 1, 1, is then the same words, so an eigenvector eigenvalue pair of this matrix 2, 1, 1, 2. So it looks like if we can take our system of equations and rewrite it as this matrix vector equation, then finding the eigenvectors and eigenvalues of this matrix goes a long way to writing the solution down. In fact, it might be all we need. So on the next board, we'll present a theorem that is this result and then do a final example. Now we're ready for our first big theorem regarding these types of differential equations. So let's suppose that A is an n by n matrix with real entries, and it has n eigenvalues that are all real numbers. So we're already restricting our setup to the case where we have real eigenvalues, but that's okay. We'll look at the other cases later. And then we'll also suppose that we have linearly independent eigenvectors v1 to vn in Rn. So the fact that they're linearly independent means that Rn has a basis of eigenvectors of this matrix A. And again, that's restricting this setup to diagonalizable matrices. But again, like I said, we'll go through the other case, the non-diagonalizable case, and the potentially complex eigenvalue case later. Then the solution to the system of differential equations given by the following matrix equation, the vector valued function y prime equals a times y, is this. So we've got y is equal to c1 e to the lambda 1 t times v1 added up to cn e to the lambda nt times vn. And these ci's are real numbers. So let's notice that the eigenvalues end up in the exponential function, whereas the eigenvectors are like the directions with which these exponential functions are pointing, if you will. Okay, so now let's look at our example. We've got y prime equals this 3 by 3 matrix times y. So this will give us an excellent opportunity to review finding eigenvectors and eigenvalues. Because notice by this theorem that we just went over, once we know those, we're essentially done in this case. Okay, so let's maybe set this matrix here, which I'm putting these yellow parentheses around, equal to A. So I'll just use this notation to say that we set that equal to A just for notational convenience. And then recall that the first step in finding eigenvectors and eigenvalues is to look at the characteristic polynomial. So we'll generally denote that by PAX, and that'll be the determinant of A minus X times the identity matrix. So that's going to be the determinant of the following matrix. I'll use these vertical lines to mean we're taking the determinant. So we have 3 minus x here, minus 1, minus 2, 3 minus x here, 2, 4 minus 1, and then negative 2 minus x. So something like that. And in order to do this calculation, we'll use the so-called cofactor expansion. So let's start by factoring across this first column in this first row. So that'll give us 3 minus x times the determinant of the leftover sub 2 by 2 matrix. That'll be 3 minus x, 2, minus 1, and then negative 2 minus x. Okay, good. Then we'll have minus negative 1, so that turns into a plus 1. And then what we get from expanding with the first row in the second column. So there we've got negative 2, 2, and then 4, negative 2 minus x. Okay, and then finally, expanding in the last column in the first row will give us a minus 1, and then we'll have negative 2, 3 minus x, and then 4, negative 1, 4, negative 1. Now we just have to calculate all of those 2 by 2 matrix determinants. Okay, so doing this carefully, we have 3 minus x, and then we'll have 3 minus x times negative 2 minus x, but a bunch of minus signs cancel there, and we essentially end up with x plus 2 times x minus 3. So that'll be x squared minus x, and then minus 6 when all is said and done. So again, this is the same thing as x plus 2 times x minus 3. And then from that, we're going to add 2. We're subtracting negative 2, but that means we'll have a minus 4 right there. Okay, so that's this determinant here. Then what do we get for this guy? And then what do we get for this term? So this negative and this negative will cancel. That'll leave us with 2x and then plus 4. And then we'll subtract 8, so it'll be 2x minus 4 in the end. And then for this last determinant, we'll have 2 plus 4x minus 12. Okay, now let's see if we can simplify this at all. And I think we can quite nicely. Okay, so this is going to give us 3 minus x times x squared minus x minus 4. And then here we'll have, let's see. And then subtracting 4 will give us plus 6. And then this 2x minus 4x will give us negative 2x. But let's note that we can factor a 2 out of that. And if we factor a 2 out of that, we have 2 times 3 minus x, which is great news because we still have a factor of 3 minus x from this first term. So that's going to give us 3 minus x times x squared minus x, and then we'll have negative 4 plus 2, so that'll be minus 2. But let's notice that x squared minus x plus 2 will in fact factor as x plus 1 times x minus 2. So that tells us that we have the following 3 eigenvalues, which I'll save up here. We have lambda equals negative 1, we have lambda equals 2, and we have lambda equals 3, as those were roots of this characteristic polynomial. So now let's find the eigenvectors. So we just got done determining the eigenvalues. Now we're going to determine the eigenvectors one at a time. So let's start with lambda equals minus 1. That's as good of a place to start as any. Okay. So recall, in order to find the eigenspace related to this eigenvalue, what we really want to look at is the null space of A minus this lambda times the identity matrix, which turns into A plus the identity matrix. Let's maybe quickly recall that what we're using here is that the eigenspace with eigenvalue lambda of A is in fact equal to the null space of A minus lambda times the identity matrix. That's what we're using here. So now we want the null space of the matrix where we've added 1 to everything on the diagonal. So that'll be 4, negative 1, negative 1, negative 2, 4, 2, and then 4, negative 1, and then another negative 1. Now we're ready to do row operations. Let's recall that row operations do not change the null space, so we can just have equality here between null spaces. So first off, note that the third row is the same thing as the first row, so we could do the first row minus the third row and have that be our new third row, for instance. That means we can take this entire third row and just replace it with all zeros. And again, like I said, we do not change the null space. Next up, I'll notice that this second row, everything is a multiple of 2. So I might as well divide that by 2 and then swap these rows. So that'll give me the null space of, so I'll have 1, negative 2, negative 1. I really divided by negative 2. And then 4, negative 1, negative 1, and then my row of all zeros. So something like this. And then next I'll finish it off by doing, let's write it down this time. Row 2 minus 4 times row 1 becomes my new row 2. Okay, that'll zero this term out. So let's see, we have 4 minus 4 is 0. So, I mean, that's by design. I'll copy my first row back over. So I have a 0 here. Then I have negative 1 plus 8. So that will be the number 7. And then I finally have negative 1 plus 4. So that'll be 3. Okay, so that's looking good. Good. And then my last row is still all zeros. And then from here, I'll divide that second row by 7 just to get me a 1 in the correct location. So I'll write this as 1, and then I can write this as 3 over 7. Then my last row operation will be to zero this term out. So that'll be gained by taking row 1 and adding it to row 2. So let's see, we'll have the null space of 1, 0. It's because negative 2 plus 2 is 0. And then we'll have negative 1 plus 6 over 7 will give us negative 1 over 7, and then we'll have 0, 1, 3 over 7, 0, 0, 0. Okay, so we've shown that the null space of this matrix is the same as the null space of this matrix. Now let's bring this up and we'll finally find the eigenvector. So this is where we left off. We saw that the null space of this matrix, which is the eigenspace that we're interested in, was the same thing as this null space of this matrix in reduced echelon form. Now let's find the eigenvector, and we can do that by pushing it back to a system of equations. So we'll take this row reduced matrix, 1, 0, negative 1 over 7, and 0, 1, 3 over 7, 0, 0, 0. Let it attack the vector x1, x2, x3, and notice that if we're in the null space, that gives us the null vector or the 0 vector. So that means that x1 minus 1 over 7 x3 is equal to 0, and then x2 plus 3 over 7 x3 is also equal to 0, whereas x3 is our free variable. Of course, we get an eigenvector just pointing in a certain direction. We scale it as needed. Notice we've got built-in constants over here, so that's kind of okay. So maybe the logical thing to do would be to take x3 to be equal to 7, since it's a free variable. And what we'll see is that means x1 is equal to 1, x2 is equal to negative 3, and then x3 is equal to 7, meaning the eigenvector going along with this eigenvalue of negative 1 is in fact equal to 1, negative 3, 7. So let's gather that up here, and then we'll skip the calculation for the rest of them as it's essentially the same and write down our final answer. So in the last board we calculated that the eigenvalue negative 1 had eigenvector 1, negative 3, 7. And then with similar methods, the eigenvalue for 2 has eigenvector 1, 0, 1, and the eigenvalue for 3 has eigenvector 1, negative 1, 1. But with all of this information and this theorem over here, we can write down our final solution. So our final solution will be a constant c1 times e to the minus t times 1, negative 3, 7. So that's from this eigenvector eigenvalue pair. And then plus c2, and then e to the 2t, and then 1, 0, 1. So that would be this eigenvector eigenvalue pair. And then finally plus c3, e to the 3t, and then 1, negative 1, 1 from this last eigenvector eigenvalue pair. And let's say you did not want it in matrix vector form or in vector form, you wanted it as y1, y2, y3. Well, you could do that quite easily. I'll do it just for y1, and that is from taking out the first component of all of these vectors. So that would be c1 e to the minus t plus c2 e to the 2t plus c3 e to the 3t. And then maybe I'll do one more just for good measure. So y2 would be equal to negative 3c1 e to the minus t, and then minus c3 e to the 3t. Again, going from these second entries. Then you could write down y3 as well. Okay, so let's leave with some warm-up problems. Okay, I've got 3 warm-up problems for you. So the first is to translate this second order differential equation to a system of first order differential equations. But don't worry about solving it. The next is to translate this first order system into a second order differential equation. But again, don't worry about solving it. These first 2 are just about translation, so that like rank order duality here. And then the third one finally is to solve this system of differential equations with the following matrix form. We have y prime is equal to this matrix negative 6, negative 3, 1, negative 2 times y. So you'll need to find eigenvectors and eigenvalues and such, and then use this theorem. And that's a good place to stop.